All right, so notes on the cross product. The cross product is based on answering the question, given two vectors, can we find a third vector which is perpendicular to the given vectors? And so we'll use A cross B to denote that vector. So here's some perspective, like this is A, this is B, A cross B could be like that. This is A, this is B, A cross B could be the green vector, right? This is A, this is B, A cross B is that vector. So each one of these corresponds to the right-hand rule. Like I take vector A, crossed into B, and pointing up. Oh man, you can't see it. Well, I don't know if I can. I think I need a smaller hand for the right-hand rule here. This is not going to work. Sorry. I showed you the right-hand rule in class. I refer you to class. Anyway, so the right-hand rule gives you all three of those. And so what I do here, and you can skip over this if you don't care, I mean, it's fine. But what I do is I just say, okay, so what we're wanting is a vector C that has a dot product with both A and B, which is 0. And maybe if I use those equations, I can derive the cross product, and I kind of sort of do. So I just, look at A dot C being 0 and B dot C being 0, and I make a few assumptions, and eventually I come to this equation that A1B2 minus B1A2C2 and plus A1B3 minus B1A3C3 is equal to 0. So the easy way to solve this equation is to make this be that, and to make that be that, but off by a sign, and then they would add to be 0. And that just so happens to be the formula for the cross product. But of course, that's not the only solution that's possible for that equation. It's just, So this is just a very, this is not an ironclad argument by any means. Like, this is just a kind of, sketchy derivation to show you how a person might have stumbled upon the cross product formula if they were just trying to work out the dot product of two vectors being 0 and constructing a third one. The more rigorous answer to why the cross product is what it is that the cross product is based on the volume, based on the idea that, I shouldn't say the volume, I should say the area. It's based on wanting a product which gives you the area that is covered. The magnitude of the cross product is the area of the parallelogram that has, side vectors A and B. So if I have like a and B, and I make a parallelogram by putting B over here too, and A over here like that, right? Well then, this is a parallelogram, and the area of that parallelogram is equal to the magnitude of the cross product. So that paired with the right-hand rule, paired with the, insistence that A cross B be perpendicular to A and B, that pretty much forces the definition that we have, all right? Actually, it doesn't pretty much force it, it forces it. So, anyway, here's the definition. So A cross B is A2B3 minus A3B2, A3B1 minus A1B3, and then A1B2 minus A2B1. Notice that the first component doesn't have the first components of A or B in it. The second component does not have the second components of A or B in it. And the third component does not have the third components of A or B in it. That's very helpful for remembering this formula. Of course, I do allow you guys to have a note card, so you don't, technically speaking, need to remember it. It would be wise to remember it because, that will make your calculation a lot faster than if you're always trying to match up with this formula. It's a pain. You need to work about 10 cross products before you get really comfortable with it. Okay. Anyway, so it's easy to check that A dot A cross B and B dot A cross B is 0. I think I did one of them in class already. And so here I'm introducing a kind of a slick notation that allows you to write a formula for the cross product really compactly. This is called the Levi-Civita symbol. Epsilon 1, 2, 3 is epsilon 2, 3, 1 is epsilon 3, 1, 2, which is 1, whereas 3, 2, 1, 2, 1, 3, and 1, 3, 2 give you minus 1. Those are the pluses and the minuses in the formula for the cross product, actually. And so with that notation, you can write the cross product simply as the sum over ijk of ai bj epsilon ijk x x sub hat x hat k. So that's a super sneaky formula for the cross product, which I don't expect you guys to know, remember, or even use. I'm just mentioning it for your information. And so like I have some proofs in this section that you can skip over if you're not interested. I've included them in case you're curious, because everything we claimed about dot products in the previous section, like they're pretty easy to work out. The formulas I'm about to state for the cross product here, they're not too hard to work out, but they're a lot easier with the epsilon symbol. So, but of course what's more important for you guys is just to know the properties. So A cross B is minus B cross A cross B plus C is A cross B plus A cross C, and A plus B cross C is A cross C plus B cross C. And of course the scalars factor out. We can pull C out and if we like. Alright, so as I say in this remark, the proofs I left here for you to understand why I care about the funny epsilon ijk notation. I omitted, though, the more sophisticated proofs later in the section for the sake of brevity, believe it or not. And you can look at my Calculus 3 notes for all the gory details if you're curious. But here's what the proof of A cross B equals to minus B cross A looks like in the epsilon symbol notation. Like this equals that. I flip the orders of B and I flip the index to get a minus. And there it is. In the brute force notation, which I think I did in class actually, A cross B is minus B cross A. It takes all this. That's not too big a difference, but you know, this right here, like the distributive, so A cross B plus C is A sub I B. So like the jth component of B plus C is A B sub j plus C sub j. And so I can prove this is equal to that in that much space. If you write this out by hand, it takes about a half page to a page, depending on how big you write. All right, so I don't know. Anyway, the properties of cross product are where they are. I know I'm more excited about the proofs than you guys are, so let me move on here. Here, A cross A, what's that? Well, A cross A is minus A cross A because it's anti-commutative, right? And that gives me that twice A cross A is 0. So any vector cross itself is 0. Okay, well that's good. Good to know. Here's a sort of symbolic problem. Simplify A minus B cross A plus B. See what happens. So we use the distributive property, you know, and then we use distributive property again. A cross A plus A cross B minus B cross A plus B minus B cross B. Of course, A cross A is 0. B cross B is 0. And so what are we left with? A cross B, and then flip that around, we get minus a minus, which gives us plus A cross B. So we get twice A cross B. So that makes like a pretty decent like homework or quiz or test question or something right there. I think I missed giving you one of these on the take-home quiz. Maybe I'll make up for it and put it in the in-class part. I don't know. Although it's kind of more likely in the in-class quiz, I just ask you to calculate dot products and cross products of numerical vectors, because that is the first order of business. How do we calculate 1, 2, 3 cross 4, 5, 6? All right, so 1, 2, 3 cross 4, 5, 6, I do. And so I'm just using the definition. So 2 times 6 minus 3 times 5, 3 times 4 minus 1 times 6, 1 times 5 minus 2 times 4, and I get minus 3, 6 minus 3. So as I say, there's 6 opportunities to make an error, at least. So it's a good idea to check your answer, and to check the answer, we just check 1 is 1, 2, 3 dot minus 3, 6 minus 3, 0. Well, that gives me 1 times minus 3 is minus 3, 2 times 6 is 12, 3 times minus 3 is minus 9. So is 12 minus 3 minus 9 0? It sure is. And you can also calculate that A cross B dot 4, 5, 6 is also 0. All right, so like whenever you calculate a cross product, you must check your answer, because don't be so prideful as to think that you haven't made a mistake. And don't be so lazy as to think you can't fix your mistake. You can. I should mention, there's another popular way to calculate the cross product based on abusive notation with what's called the determinant. So the determinant is something that we do to a box of numbers called a matrix. Here's a formula that mathematicians are scared of, but the way we actually calculate this defines the determinant for what it's worth. but the way students tend to calculate determinants is by the expansion by minors, which is due to Laplace. Here's how that goes. So the determinant of a 2 by 2 matrix is A times D minus B times C. So you take the product of the diagonals minus the product of the off diagonals. That's the 2 by 2 determinant, all right? Then to calculate a 3 by 3 determinant, this is the pattern. This is the formula. So I do A, B, C, D, E, F, D, E, A, D, H, I, G, H, I, the determinant of that. So you do, and I'm only gonna be able to do it like, so C, A, and then you pick the stuff that's not in that row and column, which is E, F, H, I, right? See that? A times that. And then the way it goes is it goes plus, minus, plus. So you put minus B, and then the determinant of the 2 by 2 stuff that's not in the B. So I will foolishly try to do that in blue. So here's the B, right? What's not in the B? This piece and that piece, right? So you put those just like they are, D, F, G, I. And then C, and the things which are not in the C, which is the leftover D, E, G, H, D, E, G, H, right? And there you have it. And then, of course, the 2 by 2 determinant, you just use that formula right there. So you get A times that minus B times that plus C times that. That's how to take the determinant of a 3 by 3 matrix, all right? And the point is that that's the same pattern, all right? That's the same pattern as we saw for the cross product, actually. So like the cross product, A1, A2, A3 cross B1, B2, B3, you can use this mnemonic, this kind of slightly incorrect formula that people understand. X hat, Y hat, Z hat in the top, X, and then A in the second row, B in the third, and you just follow that expansion by minors formula. Put the X hat first, and then A2, B3 minus A3, B2, and then you put minus Y hat, A1, B3 minus A3, B1, and then plus Z hat, A1, B2 minus A2, B1. And so this is a popular formula that students usually do pretty well with. All right, and of course you don't have to use the X hat, Y hat, and Z hat notation. You could just, you know, write it in terms of like commas, right? You could do like A2, B3 minus A3, B2. And then minus Y hat, so I'll do it the opposite way, A3, B1 minus A1, B3, and then A1, B2 minus A2, B1. Of course, that is the formula that we defined the cross product with right there. Okay. All right, so I'm trying to get some numerical examples. Here's one. So actually, this is the one we just did before, directly from the definition. Now here's how it looks with the determinant formula. 1, 2, 3, cross 4, 5, 6. So I put my unit vectors in the top row, 1, 2, 3, 4, 5, 6. Follow the expansion by minors formula, and there I get minus 3, 6, minus 3, which of course is the minus 3, comma 6, comma minus 3 we found previously. All right. So technically speaking, this is formal nonsense because you're only supposed to put numbers in the whole matrix, and you shouldn't put vectors in one row and numbers in the next. But you know what? Everybody's doing it, so I guess it's okay. Sorry, I should probably stop teaching you guys that. That's not actually a good rule for life, especially these days because a lot of people are idiots. But anyway, x cross y is z hat, y cross z is x hat, z cross x is y hat. These are like basic, the basic cross products of the unit vectors. And so if you know these three things, and I also when I often people like to do this. You do x hat, you do y hat, you do z hat. You put them in a circle, and so x hat cross y hat gives you z hat, right? And z hat cross x hat gives you y hat. And if you go opposite the circle, you get minuses, you know. So some people like that, and of course you can. In the usual notation, this is I hat, j hat, k hat for other people. I use x, y, z, but anyway, same idea. And so here is the 1, 2, 3 cross 4, 5, 6 example with just using properties of cross products like algebraic distribution paired with the fundamental cross products like x cross y is z hat, x cross z is minus y hat, and so forth to get the same thing. So the same example yet again. All right, anyway. So this is definitely the wrong way to do it for that example. Here's one where a method of example 5.7 actually makes sense. So example 5.8 here. So here I have a cross b, where b is just x hat. So this is easier because 1, 2, 3, 1 x hat plus 2 y hat plus 3 z hat. So notice that x hat cross x hat is 0, so I ignore that. So I just get 2 y hat cross x hat plus 3 z hat cross x hat. But y hat cross x hat is minus z hat, and z hat cross x hat is y hat, so I get minus 2 z hat comma 3, which in the other notation is 0, 3, minus 2, right? All right, and let me add a little value here. If we did the mnemonic one, if I can find a marker that's not stupid. Is this green? This red one good? Maybe. So I'll just write it down here. I'll try to, let's say, let me do it down here. I'm on the thing. So, all right, so here, 1, 2, 3 crossed with 1, 0, 0. Okay, so if we use the determinant formula, so we got 1, 2, 3, 1, 0, 0. So the only thing that matters is the z hat one, because otherwise, well, anyway, so fine, I'll write it out. So x hat times, 2 times 0 minus 3 times 0 minus y hat times 3 times 1 minus 1 times 0, and plus z hat times 1 times 0 minus 2 times 1. So what do you got? No x hats. How many y hats you got? You got yourself minus 3. Oh man, minus 3. What'd I do? Oh, I put 2 minuses in, my bad. It's supposed to be a plus. So we get plus 3 there. And then, now if we checked our answer, we would have caught my sign error there at the end, right? But anyway, so that of course is exactly what we found up here, this way. The other way. So I don't know, whatever way you're most comfortable with calculating it, it's up to you. I personally like actually my definition that I gave at the start. It's not bad. Here's another one of these. Cross product examples here. So we have 3, 2, 4 cross 1 minus 2, 3. So I put them in the determinant, and then I do x hat times 2 times minus 3, which is minus 6, minus 2 times minus 2 times 4, which is minus, which gives me plus 8, minus y hat, and then I do 3 times 3, which is minus 9, and minus 4 times 1, which is minus 4, of course, and then z hat, 3 times minus 2, which is minus 6, and then minus 2 times 1, which is minus 2. So lo and behold, we get 2x hat plus 13y hat minus 8z hat, which of course in the other notation is 2, 13, minus 8. All right. Okay. Moving on here. So these are the harder properties of the cross product. These are the non-trivial product properties, as I call them. This is often called the back cab identity in physics. There's the Jacobi identity, which is this basically captures the fall from associativity. By the way, the cross product is not associative, meaning that A cross B cross C does not make sense. So this is not necessarily equal to A cross B cross C, in the sense that if I put the parentheses here versus if I put the parentheses there, they don't generally have to equal. It's non-associative. And then, of course, there's this wonderful, beautiful cyclicity of the triple product identity here. If you move the letters around in the proper, like maintain their order, but just kind of slide them around, like, let's see here. So to get, I just move B to the left and C to the left, and A kind of goes back around. See that? And then I move C over and move A over, and then B goes around to get to that one. So the proofs of those are pretty tough, but let's just use them. So if you know Lagrange's identity, which is A cross, the magnitude of A cross B squared is the A squared, magnitude of A squared, magnitude of B squared minus the dot product squared, then you use the fact that we know A dot B is AB cosine theta. Well, then lo and behold, we get A squared B squared times 1 minus cosine squared, but hey, 1 minus cosine squared, we know that, that's sine squared. So take the absolute value of this, and what you get, well, what you see from this is that the magnitude of A cross B is AB sine theta. And then, of course, the unit vector n hat is given by the right-hand rule, as I believe I discussed in class. And so here's a description of the right-hand rule on paper, which, of course, never does it justice. You need to see somebody do it in class. If you miss class that day, it's unfortunate. But here's some pictures. So A and B, so A cross B, foolishly attempting it. A cross B, thumb into paper. So that's the into the paper symbol. Here, U cross V, U crossed into V and thumb into the, what had I done? Oh, V cross U, my bad. V cross U, the order matters. V cross U, thumb out of the page. So that's why I've got the out of the page symbol there. And I'm calculating the magnitude using my newfangled formula. The magnitude is AB sine theta, so it's 20, since I gave 5 and 8, 5 times 8 is 40, 40 times sine of 30 is 20. So, and here's another example. So in physics, you know, one of the main applications of the cross product is for rotational motion. Here's the deal. If you have an axis, right? And so if you have an, oh, come on. They must have different batches. They won't, these markers won't, they won't stack. What? Horrible. All right, fine. I guess I'll use the closest thing or whatever. So if you have an axis, right, and you have a positive direction, let's say like this, right? You take your right hand and you put your thumb in the direction of the axis, all right? The way your fingers curl around the axis, that's the positive rotational direction, right? So like, if you have an axis, you can talk about rotation around the axis, and the rotation is either positive if it lines up with the right-hand rule, or if you're the opposite direction, then that would be like negative. So anyway, if you take a force and you apply it to a like, you know, something that can pivot, then it turns out that the radius arm, which is the direction vector from the pivot point to where the force is applied, crossed with the force gives you what's called torque. So in this case, R should be like this, crossed into F, be into the page. So in other words, we're like this, which means that we're creating a rotational motion that's like this kind of rotation, which of course matches just common sense, right? If you push the force like that, you're going to kind of make it go that way because a little bit of the force is pushing it. And of course, a lot of the force isn't doing anything. It's just pointing, just kind of, it's like if you have a door, right, and you just press on the door towards the hinge, nothing happens, right? But if you're a little bit off the plane of the door, then you can make the door move in or out. Anyway. And then finally, I mentioned this in class, the area, the magnitude of the cross product is the area of the parallelogram, right? another thing to think about, what would it be if we, say, wanted just to calculate, let me mess up my picture here. What if you just wanted the area of this triangle? Area of the triangle, right? Well, that would be 1/2 the magnitude of A cross B, right? Because the area of the triangle is 1/2 the area of the parallelogram. So if you take half of the magnitude of the cross product, it gives you the area of the triangle, which has A and B as sides, as two of their sides. So that's a fun thing to know. That will help you with one of your homework problems. And then finally, oh man, I forgot to put a homework problem in this. If you have 3 vectors, the volume is given by what's called the triple product. So the triple product here, A dot B cross C, it's called the triple product. That actually gives you the volume of a parallel pipette, which is, what that means is it's got parallelograms everywhere, but you can define it by 3 vectors. So a cube is a parallel pipette where the 3 vectors act like pairwise perpendicular, you know. But here's what it looks like if it's more squished. So you got like A here, you got B here. So the volume of such a thing is the area of the base, right, times the height. Well, how do you get the height? You can get the height from taking, well, how do you get the normal to that? Well, A cross B has normal, excuse me, the A1 has normal A cross B, like the direction of A cross B. I called it n hat. So that points directly up, right? And then C is tilted by some angle beta. And so like C dot n hat, well, that gives you the height. So if I take A cross B and I dot with C, well, that automatically gives me the height times the base times the area of the base, which of course is the volume. So anyway, this is the triple product rule, and if you tilt your head and squint at this for a while, you can figure out why it makes sense. But that's a nice thing to know about if you want to calculate the volume. You got 3 side, so like here, for example, if we have a parallel pipette with edges 0, 1, 1, 1, 0, 0, and 0, 1, 0, we can calculate B cross C is Z hat, and then A dot B cross C is just 1. So this the parallel pipette with edge vectors A, B, and C has volume 1 in this case. So, and anyway, that's about all I have to say. So, like I said, we'll have a short quiz, start a class Monday and probably also Wednesday, and I'll try to answer questions you guys have about the take-home quiz on Monday. All right, so see you there. Thanks.